First of all, let me introduce myself. I am Ki-jung Lee. I'm working at Busan National University in South Korea, and I will moderate this session today. Okay, today, as the second speaker of Korea Data Science Colloquium, we have a very distinguished speaker, Professor Dirk Helbing, who is actually leading scholar in the world of social data science area. And let me just briefly introduce himself. He is working at the computational social science at the Department of Humanity, Social Politics Science at ETH Zurich. He is also with the computer science department. And he is also a member of external faculty of Complexity Science Hub Vienna. After his PhD in TU Delft in 2014, he stayed there for some years as a faculty member of technology, policy, and management before he joined ETH Zurich. And he started his work as a physicist, but he extended the area to social econo physics. He opened a new area for pedestrian and crowd dynamics modeling. And he published a number of papers. Some of them are published in Nature or Science or other very prestigious journals. For example, I look at Google Scholar to search his webpage, and I found that, for example, he published one of the first paper in Physical Review, and the citation number almost reached to 8,000. 8,000 is a big number as a citation number. Okay, and he is a co-founder of several research labs like CCSS and the Risk Center, Institute for Science, Technology, and Policy and Decision Science Lab. He has also contributed a lot to set up a data science computational social science in Europe. Okay, so it's a very long CV. He did a lot of things during since the last years. And today he will give a talk, and the title is How to Manage Society Better Than Optimal. Better Than Optimal, which is a very surprising title. Okay, so one thing that I would like to announce you is if you have any question, you may type it into the chatting window, then either in Korean or English. Then I'd like to translate to English. Okay, so let's welcome him with a big hand and listen what is better than optimal. Okay, over to you, Professor Helbing.
All right, thank you very much for the kind invitation and introduction. I'm so glad to talk to you. I'd like to welcome everyone, and I'll be talking about the future of digital democracy today, and I hope it will be inspiring. I start with some developments we've seen in the recent past, and among others, we've had books like this, Move Fast and Break Things. It was one of the mottos actually of Facebook at the time. And a couple of years back, people have often said similar things to this. Democracy is an outdated technology, it was claimed. It has brought wealth, health, and happiness for billions of people all over the world. But now we want to try something new. And that's what they did. Now, the question is democracy really outdated? And I'd like to argue it's not. We just need to reinvent it. There are many pillars of democracy, and I'd like to mention three of them over here. One is freedom to vote, one is secrecy of the ballot, and one is the principle, one person, one vote. So it should not be possible to buy votes with money. But I'd like to claim that this is now being undermined by profiling, scoring, and targeting. It's not so difficult to figure out what political party somebody would vote for. And moreover, it's also possible to manipulate those votes by companies, for example, or institutions or countries that would invest money in order to turn people's opinions. We are living in a time, I'm trying to switch slides, but it's not working for some reason. We are living in a time where all of us are being profiled and targeted. A lot of data is being collected about us, more than most people would actually think. People would probably be shocked about it. And we've learned about it back in 2015. It was one of Snowden's revelations at that time. And the issue is that there are actually highly detailed profiles about every one of us that reveals the personality, the character, the strengths and weaknesses of everyone. And in the meantime, we have digital doubles, avatars, or even twins, and it's possible to see anyone's personality. Now, the question is, what is being done with all that data? You know, is it really for our good or not so much? And that is a quite controversial discussion. It's not a finished discussion. It's ongoing, but things go so far that there's predictive policing, of course, in the meantime, based on all that data. And it goes so far that it would even basically police our karma. So it would really be very far reaching. And with all the data, we would also be targeted. That means there would be behavioral manipulation and control of people by means of personal or personalized information. And we've learned that from a number of people, including Tristan Harris, who has worked for some time in a Google control room, and he's given a very insightful talk at the tech conference, and it's entitled How a Handful of Tech Companies Control Billions of Minds Every Day. This includes, of course, our minds. And the question is, do we want this, and is it really for good? We've then learned about the Cambridge Analytica scandal, where, for example, the Brexit vote was manipulated in this way. And we can really speak about propaganda AI in this context. It's weaponized and it knows us better than we know ourselves. And that was already many years back. In the meantime, we have digital twins, and these digital twins may contain a lot of health data. It may contain a lot of data about what we do and what we think and how we feel. And the idea for some time in some countries, at least, was that we could basically simulate the entire world in a computer. And it would be a huge agent-based simulation, and those agents would be personalized. That would be kind of learning black boxes that would be fed with surveillance data about every one of us to create digital twins that behave very similar to us. And in this way, we could basically simulate the future or alternative futures and choose the best of all futures and basically implement it or impose it on the world. And that has created something like a control room approach. The military is using that, but not only them, it's also all sorts of tech companies that have a very similar spirit and approach. And so the question really is, can we now fix the world with a control room approach, with all that big data and AI systems that we have now at our fingertips, in a sense? And could the military make a prediction machine? Proposals have been quite far-reaching, so far-reaching that some people have proposed we would be able to automate society, not just cars and machines and production and robots, but basically automate society to the extent we would not even take decisions anymore. We wouldn't vote. We would live in a post-choice society. And that is quite shocking to some people. And the question is, would it really be good for society? Would it really be good for us? Could society really be run like a machine? And I like to argue that's not going to work well because society is a complex dynamical system, and complexity has all sorts of implications. And while digital twins work well for infrastructures and also production and some other areas, they have limitations when it comes to people's psychology, health, to society, and to ecological systems, and any complex dynamical system. And I will go into more detail in a couple of minutes. And I think that was perhaps also one of the reasons why the so-called godfather of AI, perhaps we should even think of him as the father of a godlike AI. He was leaving Google and he was warning of dangers, actually, of that kind of technology. Why did that digital twin approach kind of to create a digital copy of the entire world and then try to find an optimal solution and impose it on the world, why did not work so well? Not perfectly enough, I would say. Well, there are measurement errors, there's limited confidence, there's uncertainty, there are sample biases, there are classification errors, correlations do not imply causality. Sorry for the spelling error over here. There are computational limits, NP hardness, for example, overfitting, black box algorithms, non-convergent learning in some cases, non-robust models, context dependence, ambiguities, a halting problem, undecidability, and incompleteness. And finally, sensitivity, butterfly effects, deterministic chaos, and turbulence. And I'd like to go into those complexity-related issues for a moment. So everyone knows, I guess, the game of life. It's based on 3 or 4 very simple rules. It's a cellular automata, and it behaves sometimes in a quite surprising way. So the dynamics does not look so easily predictable. And of course, you could use machine learning to try to learn this dynamics. And even though the rules are simple, it is very difficult actually to reconstruct the original rules that produce that dynamics with machine learning. You could approximate it with machine learning, certainly, most likely with a lot more parameters than are in those 3 rules. And so some problems are very difficult to learn. We need to realize that. And then also complex dynamical systems may really behave quite differently if we just change parameters a little bit. And you can see over here 3 different behaviors, if you like 6, but in principle, different behaviors by just changing parameters a little bit in a simple pedestrian model. Now, complex systems are all around us. There are a lot of examples. Turbulent fluids, traffic flows, large supply chains, social, political, economic, and ecological systems, financial markets, group dynamics, and crowd behavior. And there are limits of predictability as we know it actually from weather forecasts. So, even if you had 1,000 times more data, the forecast would not get 1,000 times better. Even if you had 1,000,000 times more data, you could not predict the weather for an entire year. And why am I saying that with confidence? Because we know some of the underlying equations of what produces weather. And there is the physics of turbulence behind that. And we know that turbulence implies that little changes could actually, over time, have large effects. And this is something that turbulence shares with another kind of problem called deterministic chaos. And it appears even in mechanical systems without any noise and uncertainty, such as that double pendulum. It's an extremely interesting, inspiring, almost shocking example that shows that the slightest change in the, for example, initial conditions could over time really lead to dramatic differences in the further dynamics and behavior of the system. And this is called the butterfly effect. And in principle, it means that in complex dynamical systems such as chaotic systems, very little changes after some time could have really huge impacts on the future of the system. Furthermore, complex dynamical systems are hard to manage and control. Here I'm showing you Lotka-Volterra's equation of a predator-prey system, it's a very simple ecological system, and we assume that there's, say, a hunter that wants to get the system towards the red cross by interfering with that system. And turns out that as he tries to do that, or she tries to do that, it will end somewhere completely else in a very different point. So these are the challenges, and there are more of them. And many people know this example of the so-called phantom traffic jam, where cars are supposed to drive in a circle. And it's not a very difficult task, but still, if the density is above a certain level, people will fail to move smoothly. After some time, a traffic jam will emerge, a stop and go wave, in fact, because little variations will actually amplify, and there will be a cascading or domino effect that eventually produces that traffic jam. We talk here about systemic instability, and it implies that even if everyone wants to do the best and has all the information and good technology at hand, everyone ends up failing. Everyone does something that they didn't want to do. And there is an outcome that we don't wish to have. Now, on the other hand, complex dynamical systems also allow for new kinds of management. And I like to illustrate that in the next slide, where we have traffic flows on the freeway, and I show you a simulation of just that stop-and-go traffic that we've seen before. However, after some time, we'll leave this car and take a helicopter in order to see what causes this stop-and-go traffic over here. And it will turn out that there is actually an on-ramp. So cars are trying to get on the freeway, and that produces little perturbations in the flow, which are then amplified, as I explained it before, and cause the stop-and-go traffic. Now, assume that the cars would be equipped with radar or laser sensors that measure the distance and relative velocity and allow the cars to accelerate and decelerate autonomously. And even if we had only 20 or 30% of cars equipped with that, we could run that system in such a way that it manages to dissolve the traffic jam, as you can see over here. We still have the same inflows, but the traffic jam is gone. And the question is, how did we do that? Even though we don't have a traffic control center that controls every single car. Well, we have changed the interactions. We call that mechanism design. And it's the interactions that determine the outcome of the self-organization and the collective pattern of motion that results. And that means by mechanism design, by changing the interactions, we can change the outcome. And the system will produce that outcome by itself, by self-organization. All we need is real-time data and real-time feedback that would change the acceleration and deceleration behavior just a bit. And so this is good news, and it will be important for everything that I will explain later on. So yeah, it's important to point out that the properties of complex dynamical socio-technical systems have often been ignored. Traditionally, we think that it's the nodes of a network that are important, and the properties of those nodes, be it people or companies or cars. And we just need to understand the properties of those components of a system, and then we would understand the system. But that's not true, because the interactions not only influence what happens in the system, but if we have a lot of interaction or strong interactions, then they would dominate actually the outcome. And it could go so far that actually it's not anymore that important to know the properties of the components, but it's more important to know the properties of the network to understand what happens in the system. In any case, in a network systems, you don't always get the intended effects. You would often see side effects, you would see feedback effects and or cascading effects. And so a little perturbation in the system could eventually really mess up the entire system. And while this is a nice experiment for a rainy weekend, these kind of things actually happen in reality. For example, the financial crisis was characterized by the failure of one bank. It was Lehman Brothers at the time, and that triggered an entire cascade of bankruptcies of other banks and losses of hundreds of billions of dollars. So given this, we really have to change our thinking about our world. We're coming from a time where we did not have enough data to take good decisions. And with big data, we can actually do evidence-based decision-making. However, there are some issues. Processing power, we are being told, increases according to Moore's law, doubles every, say, 1.5 years or so. But data volume increases even faster. And the consequence of that is that a lot of data will never be processed. We could call that dark data. And as a result, we actually need to choose very well which part of the data we would process and how. That percentage of dark data is actually increasing over time. So things are not getting better over here. But an even bigger problem may be that as we network the world, there is a combinatorial explosion of the complexity of the system. And that means complexity grows even faster than the data volume. And of course, also then processing power. That means even though we have the best technology ever and more data than we had in the entire history of humankind, it turns out that we're losing control of complex systems, of the complexity of the world as time goes on. So top-down control is expected to fail and we need a new control paradigm. Fortunately, there is one. It would be distributed control and self-organization. So that implies a new paradigm. We need to go from control to coordination. And here's a video that I recorded a couple of years back in Egypt, and I found that very inspiring. You see highly diverse traffic, no traffic lights, no police, but it works. There's self-organization going on. It works because we have unidirectional flow in the front, the opposite unidirectional flow in the back, and in between a little buffer that allows the participants to adjust the speed in such a way that they would find a gap to cross the unidirectional flow when they need that. And so how could we use self-organization to solve traffic problems? And here we have been inspired actually by pedestrian flows at bottlenecks, which often show those oscillations in the flow, as you can see it in the video. And that oscillations can be understood by a pressure principle. We've then said that intersections are, in a sense, also bottlenecks for traffic flows, just for more different directions. And we had the idea that it was perhaps possible to define something like a traffic pressure in such a way that it would produce oscillatory flows by self-organization. And we could use that to define traffic signals. That means the traffic flows would actually control the traffic lights rather than the other way around as we have it today. And it turns out that this approach can work quite well. You see over here green waves that do emerge based on such an approach. And what we do basically is we measure the outflow of vehicles from a road section, but we also measure the inflow. And based on that inflow, we can make a very short-term prediction of how many cars would be in the queue and how many cars would have to be served in order to minimize waiting times. Now the question is, how well does that actually work? And we have compared basically 3 different approaches. The traffic control center approach on the left is what we have today, basically. Traffic control center would try to collect as much data as possible, come up with an optimal plan, and then impose it on the system and would try to coordinate traffic flows. However, it cannot really strictly optimize in real time because it's an NP-hard optimization problem. So it simplifies the optimization problem and throws away a couple, actually a lot of solutions, and we don't know how good they would be. In the middle, we have a different approach. It's decentralized, no traffic control center used over here. The intersection strictly optimized, minimize travel times based on the inflows from the neighboring road sections. And we could call that a homo economicus approach because each intersection strictly tries to do the best, but does not care about other intersections. And then on the right, we do the same thing, but in case there is a long queue, we would first clear the queue before we go back to travel time minimization. Now, according to classical intuition, we would think the left approach, the central optimization approach, should be the best. It coordinates activities in the entire system. This middle one should be the second best, and the third one would be the worst, which is other regarding, doesn't care about the own performance that much. And let's see what really happens. Now, the red line corresponds to the top-down regulation by a traffic control center. Queue length grows with capacity utilization. That's expected. And let's see what happens with the homo economicus approach, the selfish optimization. And that's represented by the violet line. And you can see this is much better for low capacity utilization because cars basically get the green light when they approach the intersection. But there is a capacity utilization around 0.6 where the queue length starts to explode and things get out of control and the monster traffic jam results. So that doesn't work for high traffic volumes. However, the third approach, the other regarding optimization or self-regulation, that is actually performing better all the way. Perhaps quite surprising for some, and you could say, okay, that's computer simulation based on perhaps some simplifications, and how well does that really work in reality? And in fact, it has been implemented in a couple of cities, including Dresden and Lucerne. And it was then even framed as a super traffic light. I should say I was not involved myself, but my previous PhD student who is working with me on that, he has established a company with the previous person running the traffic control center in Zurich, and together they came up with this self-control, and look how it performs. Now, there is actually an improvement for all different traffic modes, for all traffic participants, and it's quite substantial. We can also see it over here, where we have a comparison of the resulting green waves. On top is what they had before, but there's a lot of waiting time, which is represented in red. And on the bottom, you see it's less regular based on the self-optimization approach, but a lot less waiting times because it's more flexible. It really adapts to the needs of the traffic flows. And so this can be used in order to improve traffic flow for everyone, but also to have a positive environmental impact. And the conclusion overall is we cannot or we should not control everything top down. Now, what are the implications of this for other complex dynamical systems, such as our society? I'd like to say that informationally assisted self-organization works well, is efficient and resilient, can handle reasonably large deviations and perturbations, which is actually compatible with freedoms, and also with democracy and human rights. And that makes the approach particularly interesting compared to a top-down control approach, which is not well compatible with freedoms and democracy. So how to make democracy work? How can we upgrade democracy with digital means? And there are many things we can do. Unfortunately, I can only shortly touch upon those, and there's a lot more. We do have a collection of papers on digital democracy. You can find them through our webpage. So we are working on this since 2015. And I'd like to say that democracy, from my point of view, is about enabling distributed knowledge and collective intelligence, also collective action, actually. So how to make that collective intelligence work? We know about swarm intelligence, and it's very fascinating to most people, right? So we've seen those birds, flocks, and we really wonder how they do it. You know, if just imagine those were airplanes, you know, most likely you would not fly with an airplane if it was that dense, and birds can just do that. You know, it's amazing. But the principle of swarm intelligence can be extended to collective intelligence, and there are many books about the wisdom of crowds. And the question is, how can we harvest that? Back in 2015, we have written perhaps our first paper on this, Build Digital Democracy. And altogether, what we want to achieve is to bring the best ideas of many minds together. And in order to make sure that there's not a madness of crowds in result, it's important that the process is structured in a certain way. Phase one should be a phase of independent exploration, where people independently of each other and not manipulated in any way, also not by personalized search engines, where people search for information and for solution approaches independently of each other. It's important that they come up with many different perspectives and approaches. In phase two, they sit together and there's information exchange. They learn from each other, they compare their solutions, but that's not the end, because in phase three, they would start to improve solutions, to combine solutions, and that happens in a deliberative process. And in fact, there are many examples that illustrates the power of this approach. Among them, the famous Netflix prize, where they were trying to predict the favorite movies of people based on ratings. And it turns out it was a difficult task to get better than the company itself. And it took a long time actually to jump over the threshold that was required to get the $1 million. It turns out that none of the teams managed to do it by themselves, and it only worked when the best team combined their solution approach with other solution approaches that were not as good as their own one. That means you would think the combination of the best with less good solutions would make the best solution worse. But just the opposite happened. It improved the overall solution. And then other teams also combined their solutions with each other and improved the resulting solution also a lot. So it's diversity wins, not the best. If we have complex problems, we need to combine different perspectives and solution approaches. And so this has really important implications for how we should organize collective decision making. Compared to a surveillance-based, data-driven, AI-controlled, benevolent dictator approach, things would have to change. A benevolent dictator would perhaps, most likely, actually, things to be plannable, predictable, and controllable. Well, as you can imagine, that is not always well compatible with democracy and freedom. So there's a problem. And furthermore, that approach would probably try to determine individual utility functions. That could be done, of course, with all that surveillance data, at least approximately. And then an average utility function would be determined. Why that? Because if you want to optimize, you need a one-dimensional goal function. And a multidimensional goal function is not really working. And that is kind of the characteristic of optimization approaches, and also a limitation. And that's kind of the key to my claim that we can be better than optimal. You'll see that. Yeah, the system would try to find the best solution to the average utility function, and that optimal solution would then be implemented in the system. But you can imagine that an average utility function does not serve many people so well. And sometimes it can produce even quite bad solutions for some people. Besides, societal needs are multidimensional. So goal functions, no matter how complicated they may be, could be indices of several goals. But in the end, it's still an oversimplification of what society needs. We want to achieve improvements in many different dimensions at the same time. Prosperity, we want, sustainability, health, education, culture, and many more things, right? So this is the issue. Optimization sounds optimal, but in fact, it's based in principle on a goal function that tends to oversimplify the needs. So how else then can we take collective decisions? Well, actually, we can vote. And voting, that is really important, does not require that we agree on a goal function or a utility function. We could have different people or different interest groups with different goal functions, and still they can vote, and there's a result, and that can be implemented. And I will tell you how to do it in a way that allows many different groups to benefit at the same time, which I think makes the approach better than optimal. So it turns out, and that's very important, that majority voting is actually among the worst voting methods ever. And that's why we should replace it by other voting approaches. There are many issues, and among them, I want to explain one of them over here, which concerns cities that have many districts. And suppose we have to decide about how to invest money in the city, and we take votes, and basically those districts with most of the voters would most likely get most of the money. And other districts with less voters basically go away with little money. And this leads to the situation that in many cities, most money goes to the center, the periphery is being neglected. And in some countries, that has led to really difficult social situations. In France, for example, in many cities, we have banlieues, really social issues in the periphery that are very difficult to handle. So we need, but we can also come up with better voting rules. In order to see what we can do, I'd like to summarize what is actually the process of voting. So the process of voting is trying to summarize voter preferences in some way. And for this, basically, people vote. And this they do with a ballot at the moment, but it can be done in different ways. And those expression of the preferences, which of course comes with some degree of simplification, that would go into the ballot box. And after that, a vote aggregation is being done, which produces a democratic outcome. But in principle, there are at least two steps that can be varied. And one of them is the voting input, how we express voter preferences. And the other thing is the vote aggregation. In order to learn about different voting rules, we have created a vote app. And this allowed to vote in different ways, and we could compare those different ways. And I will present just a few voting inputs that are quite common around the world to give you an idea. So approval voting is one where you have different options, and you basically tick the options that you like, and then this goes into the ballot box. There's also combined approval voting, which allows you to express approval by 1, abstaining or disinterest by 0, and disapproval by -1. And that also goes then in the ballot box. Further on, there is ranked voting. Here you rank the options in the order that you like, in the order of your preferences. It's being translated into the numbers of points, and it goes into the ballot box. And finally, there's, of course, a lot more voting input methods, but I'll leave it here. There's cumulative voting, where there's a certain number of points that you could distribute over different options. And you could give several points to the same options, expressing how much you like a certain option. So the degree of your preference can be expressed. And that would go into the ballot box. Now, what would happen in the aggregation step? Also, here, we can actually do different things. And the most common thing is majority voting, where basically those solutions that get most of the votes would be chosen and implemented. Let's assume that we have a problem with limited budget, so we cannot do everything. And in this case of majority voting, we would go just for the options that have most votes. We would not pay attention at all to the budget. You can imagine that could be an issue. In the participatory budgeting, it's often that the costs are also considered. And in principle, what you can do is you divide the number of votes by the cost of the proposal. And then you get a ratio. And you would basically choose those projects that have the best ratio between votes and costs. And that gets you some other projects that would be approved. So there's a different outcome by considering the ratio between votes and costs. And then a third approach would be that of equal shares, where each voter would have a virtual budget that would be distributed over projects, and projects that get enough money to be realized, they would be implemented, and the others not. Things are more tricky because there's some leftover budget by those projects not realized, that would be redistributed. But in the end, we have basically 3 different aggregations. Of course, there are also more methods over here. But the important point that I'd like to make is that those aggregation methods would lead to different distributions of outcomes. And for the majority voting, it often happens that there's one big project that basically eats up most of the budget. There's basically almost no budget for all the others anymore. While some of the other approaches are a lot more equally distributed, so there's a higher number of projects that benefit, and that also means a higher diversity of projects and interest groups that benefit. And so far, I've been talking about theoretical things, but we have also actually tested that in a real-world implementation. Participatory budgeting is quite favorite since a couple of years, is being used by many cities around the world. It's popular, for example, in the city of Barcelona, but many more. And we have done that now in a small Swiss city, but we have modified the voting rules according to what we figured out to be seen the best approach in a laboratory experiment. And that has then been rolled out in this real-life experiment. This participatory budgeting exercise was called Stadtidee. Stadt is town, and Idee is idea. And basically, there were many meetings where citizens of the city were invited for deliberation workshops where they could brainstorm. And we've been using, of course, all sorts of digital tools such as Mentimeter to basically trigger that brainstorming process and summarize also the outcomes of that brainstorming process. And eventually people came up with ideas, and those ideas were basically put on the map of that city. So you see all the sticky notes at the places where projects were proposed to be implemented. And it started with more than 100 ideas. And over time, over several workshops, those ideas have been worked out in more detail, have been checked for feasibility. Some of the projects were merged, or some teams were actually starting to work together. And eventually, there were 33 projects that came on the ballot. And then there was the voting. And we made sure that there was a high transparency about how projects would be selected, because transparency is needed for trust and for support of the process. And then we applied the cumulative voting with 10 points. And we explained that it was important to have not only a certain number of votes, but that the votes would also be in good proportion to the budget that the project would cost. And this led to a cost effectiveness of the projects, because nobody wanted to risk that their project would not win because it was made more expensive than needed. So finally, there was this countdown, points were distributed over projects, and there was an outcome, and I presented over here. You can see that most of the projects were characterized, these are the red dots, by a particular good ratio between the number of votes and the cost of the project. And those projects are now being implemented. There are 17 of them. There's a high voter satisfaction. And importantly, we did compare our new approach with what would have been the outcome if majority voting would have been applied as usual. Majority voting would have supported only 7 projects. And those projects, you can see it on the left, would have been concentrated in the center. All the other districts would not have received any money. With our new approach, rather than 7 projects, we had 17 projects that were supported, and those were distributed over all districts. There were no district that didn't get any money. So there was a lot more spatial fairness, a lot more diversity, a lot more happy people. And besides, we should say that we also had greater representativeness. There were more female voters than usual. There were more younger voters and more elderly people than usual. There were also more foreigners. That means there was a larger level of engagement altogether. People were trying to make a difference, were trying to improve their city. And so, in conclusion, I'd like to say democracy can be upgraded. We had more projects, we had more resourcefulness, we had more participation, more inclusion, more transparency, more trust, more satisfaction, and more fairness. So I think it's okay to call that better than optimal. And so one should implement more democracy, I think, not less. Democracy should be about pluralistic solutions that support collective intelligence and catalyze benefits for many. We should think about adaptation rather than prediction, co-evolution rather than planning, cooperation rather than control, more than we do it today. And then the question is, can it be efficient if more people are involved in collective decision making? And here we have also been working on something, a project that basically tries to come up with new solutions to problems, but based on peer production and a particular way of co-creation that we call remixing. Here we assume that all the solutions that are being created can be modified by anyone. In this way, we basically get new and better solutions, and so all the solution approaches may evolve over time, at least those that are popular and that find engagement. So we start with perhaps one solution draft, and then it splits up into two alternative drafts, and that splits up again. So this is how things would evolve. And the question is then, how do we select the projects that would finally be implemented? And if there were a lot of projects, nobody could really look into all of these projects. It would just be too time consuming. So what we do is a peer review or distributed voting, where everyone gets to see 10 of the proposals, say, and then ranks those 10 proposals. And based on that, we create a short list of the top 10 solutions. And this is what everyone then votes on. And each of these steps is created in such a way that it does not consume too much time. In fact, it turns out that having more people engage in this process will create better outcomes. It will be more efficient. So in principle, this is, I would say, really revolutionary because it allows us to co-create in ways that are more participatory and lead to better outcomes and are more efficient. But we need to think about more openness. This is really about open innovation. And again, I say, if you want to be better than optimal, this is the way to go. We've also gone a step further, and we have actually applied voting to traffic light control. This sounds like really unexpected, perhaps, to many of you. But the idea is that some people may want to minimize travel time, and others may want to maximize speed. Others may want to minimize CO2 emissions. Others may want to minimize number of stops, whatever. So people may have different goal functions. And at each intersection, we may have a different mix of people who want this or that, different distribution of goals. And so we assume that the cars would be told what goal function should be applied, and at each intersection, the intersection would consider the mix of cars and the goal functions that they want to be pursued. So there's a voting. Of course, it could be automated, and each intersection at each moment in time basically changes the mix of the goal function to be more adapted to what people really like and need. Now, why should we do such a thing? Well, because it really has benefits. What we often do with optimization is that we try to find 100% optimal, say, efficient solution. But then if you look into the performance with regard to other kinds of goals like resilience or sustainability or whatever, it often comes with a poor performance, way below 100%. The voting-based approach that I just explained to you will deliver an approach that performs highly on different goals. Not 100% on any dimension typically, but say 80% or so on many dimensions. And that's a lot better than if we have 100% performance on one dimension and pretty poor performance on other dimensions. So these are a few of the things that I'd like to propose. I'd like to encourage you to be really a game changer, to change our future. And if there's some minutes I still left, I have some further slides. Otherwise, we can
okay.
stop it here.
Yes, that's okay.
I should go on?
Yeah, you're okay.
All right, thank you so much. I'd like to explain one more idea about collective intelligence and collective action that we've been working on. We called it City Olympics or Climate City Cup. And we all know that there are really big problems to be solved on planet Earth, many of them environmental issues, financial crisis, migration, sustainability, overcome war, find world peace. You know, these are just some of the really big challenges that we need to find solutions for. And there's the approach of the nation states and United Nations on the one hand. I call it approach one. There is the second approach, which is based on global corporations, but both have not delivered the solutions we need on time. And therefore, I think we need to have at least a third approach, and this would be the City Olympics, based on the concept of do it yourself and do it together. So in principle, we could have cities and their stakeholders and citizens work on better solutions to those problems that we need to solve. And we could have cities compete with each other. We know that competition often leads to better outcomes, higher performance. But the City Cup would not just be about winning against each other. It's actually about winning together. And the idea is that there would not only be different disciplines, like, behaving in a more sustainable way, coming up with renewable energies and all of these kind of things, whatever is really of considered to be of importance. There would also be a cooperative phase. That means the idea would be that the solutions created in those City Olympics would be open source and would be Creative Commons. And so each of those solutions could be taken by companies, by institutions, by other cities, by citizens, and developed further. They could be combined with each other. And in this ways, really global collective intelligence could emerge. So all those solutions developed by cities could be networked together in order to make quick progress and find fitting solutions for every city. And every city is different. That's why adaptation is needed. So overall, we would have a new approach that I call localization rather than globalization, because it's about thinking global but acting local and diverse and experimenting, trying out many new solutions, evaluating them, learning from each other and helping each other. And I think that would be really very helpful. We've been working on that also ourselves. We've created, for example, air quality sensors, and we've tried to make it as much open source and open hardware as possible. We've been also using maker spaces, and what we want to have is that basically everyone can, as much as possible, produce things by themselves, make measurements about the environmental conditions, improvements made, and so on. Of course, apps would also be created in that connection. And we had a first Climate City Cup back in 2019. And then unfortunately, the pandemic came. But I still believe very much in the idea and the concept, because it would combine the success principles of various systems of competition, as we know it from capitalism, of collective intelligence, as we know it from democracy, of experimentation, selection, as we know it from evolution and culture, and of intelligent design, as we know it from AI. And we could apply that, of course, in order to make our world more sustainable in a participatory way. I guess that all of us, or most of us, agree that it would be good to turn wasteful supply chains into a circular economy. Unfortunately, we haven't been that successful so far by regulation. And the question is, couldn't we do it in a different way? And in fact, yes, we could use the Internet of Things. Of course, that's happening to some extent already, but we should do that in a participatory way. Together, we could actually map noise and CO2 and all sorts of environmental poisons and materials, resources that we could recycle, externalities altogether, good and bad ones. And we could then increase positive externalities, that would be the goal, through incentives, reduce negative ones, and ensure a fair compensation. And now the proposal that we'd like to make is to do that not only by one kind of currency, like today, basically, we try to calculate a price for externalities in, say, dollars or whatever kind of currency, but it's basically all mapped on a one-dimensional currency. And I think that's not going to be effective. Instead, we should have multiple currencies, and it's easy to define new currencies by new measurement procedures that would be based on sensors like Internet of Things. The different measurement procedures would define different currencies and different incentive systems, and they could be used complementary to each other. And why do we do that? Because this is how nature works. I will come back to this in a minute. With these new kind of incentive systems, we can create new forces in our economy that would incentivize little changes for better. So everyone would basically try to improve their procedures based on their environment. And the environment would also try to improve, other companies, other people would improve in response. And so everyone would be improving in a co-evolutionary way. And that would basically change the system eventually into a circular and sharing economy. Again, it's a multidimensional approach, not a one-dimensional approach. And that would really change things quite a lot. Today, we often have typical supply chains that look like this. If you turn it around by 90 degrees, you see it's a hierarchical supply chain. It's kind of, in a sense, linear. There are no loops in it. And this is because it's made for control. And if you look at how nature does it, it looks very different. And there we go. Here are the cycles, and the cycles we'd like to have. This is a metabolic network. That means the supply chain, in a sense, in a body of a human, say. And you see, it really looks extremely different. And in a cycle, it's really not easy to say, or even impossible, does A control B or B control A, or do they basically influence each other? I think it's the last thing that happens. And so it's not a control, but the mutual feedback process that happens. It's something very different. And that's why we need to have a different approach if we want to have circularity in our supply chains and with this more sustainability. So it's a system that would basically be built on symbiosis, and that's what we need to learn, how to increase the number of symbiotic relationships in the system. And with this, I'd like to end, and I'd like to encourage you again, be a game changer. And if you have a little time and interest, then you may want to look into this book. And the link below is a collection of works on digital democracy. And I hope you will find it very inspiring. Thank you so very much for your interest. And I'm now available for your questions.
Okay, thank you. Thank you very much for this wonderful talk, and it is very inspiring. So
Thank you.
that is great. And this book is available through Amazon.
Yes.
Okay, thank you.
It looks a bit, it looks a little bit different, the cover, you know, that was our own
Right.
design proposal, and there's light coming out from the broken matrix, as you can see. And the actually book cover doesn't have the light, but I think it's important to imagine to be there, you know.
I hope it is not so expensive.
No.
All right. Okay. So thank you again. And it's time for Q&A. So if you have any questions, so you may ask it directly through your web camera and microphone, or you may type it into the chatting window. Then I will translate it. 혹시 질문 있으시면은 직접 하셔도 좋고, 아니면은 저기 채팅창에다가 쳐주시면은 제가 번역을 하겠습니다. Right. So actually, so personally, I have a lot of questions, but I'd like to begin with my some questions. So this is very interesting, and you introduce a lot of very interesting ideas. And one of them is like a collective intelligence or self-organization. But I wonder, some case from the very conservative viewpoint, the optimization is to avoid the worst case. Let me explain that. For example, in an intersection of traffic, then if we have a totally decentralized approach, then in some case, of course, it is very low probability, but in some case, we have a kind of deadlock. If you have own personal goal and objective function, then we cannot manage to avoid the worst case like a deadlock. So I'd like to ask how you think of that. So in actually, so for example, yeah, so that is my question.
All right. In fact, a deadlock could happen at a typical classical intersection, particularly when traffic lights kind of have a blackout. But not only, we see it in many cities today. What I propose is basically to design systems that would support self-organization. And in the case of the intersection in a city, the design element doing that would be a roundabout. And that means it's not enough just to let people or system elements do what they like. We need to provide the right infrastructure or hardware that supports self-organization. We also need to provide suitable information to allow people to take good decisions. So it requires a sufficient degree of information sharing, and that information would also need to have sufficiently high quality. So There are some conditions that need to be met in order for the self-organization or the collective intelligence to work.
All right. Okay. Thank you. All right. Any question from the audience? You may type in the chatting window. 한글로 그냥 거기 쓰시면 제가 말씀드리도록 하겠습니다. 질문 있으시면은 자유스럽게 부탁드립니다. I think your talk is rather than to the graduate student of data science. It is rather some politician or decision maker. Yeah. So do you have any dedicate or special message to the students who are studying data science?
Right. I think really this is an exciting age, an exciting time where we have now so much data about everything available. But it turns out that sometimes things can go wrong with analyzing data. We should not just trust data blindly. Certain things can go wrong, and we need to pay attention how we look at data. And that makes the difference between, I would say, data analytics and data science. I would also say that it's very useful, if not even necessary, to have some domain knowledge to make the best out of a certain data set and to interpret it well, to use it well. I'd also like to say that sometimes if we have too much data, we don't see the tree for the forest. So we can be confused in a sense. It could be, for example, overfitting. Sometimes it can be more powerful to combine 2 or 3 smaller data sets than using one big data set. So things are quite sophisticated. That makes, of course, the field very interesting and challenging also to some extent. So, I hope that you're enjoying this field of data science quite a lot. I'm also giving a course on data science. I think some of those lectures may be online also in our Computational Social Science ETH channel. So if you want to look it up, you're very welcome.
Okay, thank you. There are some questions from chatting window, so let me read it. The first one is from Professor Ino Hong from Jeonnam University. So he said, thank you very much for the fascinating talk. I have 2 questions. Number 1, could you give us some example of a real-world system in society that can benefit from self-organized coordination other than traffic or democracy? All right, this is the first question. And the second one is, what were the obstacles when you implemented your new voting method?
Okay, so first of all, I've basically been working on context dynamical systems for several decades now. We've been applying this kind of thinking to management of pedestrian flows at big events where there could be tens or hundreds of thousands or even millions of people interacting with each other. So safety of mass events, you know that very well because of crowd disasters that have happened in the past. The management of crowds is a challenge, and the knowledge about the self-organization phenomena in crowds can be quite helpful to make the situation a lot more safe and manageable. This is one application. Another one would be in logistics. We've been working on that. Been working on certain machines used in chip production, semiconductor production. And we have used a paradoxical effect that we call slower is faster effect in order to improve the throughput, actually quite substantially, more than 30%. So the company was very happy about that. They tried to improve their process by themselves before. They didn't manage to get it to that level, and it really made a big difference. We produced also some results for package production in a paper company. We have been working on apps for consumers, and that would basically incentivize them to behave in a more sustainable way, consume other goods. We have been creating platforms for epidemics, information feedbacks that would basically help people to decide when would be a good idea to vaccinate themselves. So we have been applying it quite through a number of different systems, and it always comes with a different perspective. And the solutions are therefore different, but I do think there are many examples that show that this approach really has additional benefits as compared to many other approaches.
All right. So
the second question was about
obstacle.
obstacles. Well, actually, we've been collaborating very closely with the city of Aarau. There were a number of people supporting the process, and everything we did was in very close collaboration with them. I would say it was pretty smooth. But perhaps what you want to hear is that not always is it simple to get those complex designs-based, self-organization-based approaches implemented, because politics today and also business, I think, is used to decide in a top-down way. And this is what we have learned. And we don't know it differently. I think that the young generation perhaps is exploring new ways over here. That makes me hopeful about the future. But yes, we really need to learn to think differently about complex dynamical systems in order to come up with better solutions for the world that would benefit us.
All right. Okay, thank you. And we have another question from Seonnam University from Hyungjae Lee. So the question is, what I learned today feel like a paradigm shift, mitigating the limitation of a dominant data-driven approach by adopting democratic solution facilitated by various voting rules. I have a similar question with the previous one from Professor Hong regarding the potential risk of applying these methods or systems just as a democratic system or collective intelligence way do not always work effectively in every age or society. Regarding this, I am curious to hear your thoughts on potential risk and any possible solution to mitigate these. All right.
Right. So as I've pointed out, collective intelligence does not happen by itself. One needs to apply certain kind of procedures for collective intelligence to come about as a collective outcome based on self-realization in a sense. If those rules are not applied, there can be chaos, and there can be the so-called madness of crowds, so outcomes can be quite bad. And in particular, those who don't believe in democracy or want to exert power, they often like to initiate and trigger that chaos, in order to delegitimate democracy altogether. So they're trying to hack democracy in a sense, to create chaos. But I should say that every system is hackable. Now, there are always two sides of a coin. And every rule has kind of some side effects that can be used or misused or abused. And you need to protect against that. This applies, however, to every single system in the world.
Okay, thank you.